Hi, it's Mr. Mac, and we're in the science lab, and we're going to observe some changes in the motor effect. We're going to be using this equipment here.
Welcome to Mr. Mac's Physics channel. He can explain things really well and is a lot of fun to watch.
Here's the equipment that we're using. It's got a magnet, a copper wire, and a rheostat, a power supply. There's scales for measuring the mass, and of course wires and alligator clips. I want to make sure that the wire is completely clean and clear at either end. So do one end, turn it over to the other with sandpaper, making sure that we can get rid of any oxidization or resin that's on there, and it's really a good connection with the alligator clips. I'm going to set up the circuit. Start with the positive side, plugging in the rheostat. A rheostat is just a large variable resistor. I'm plugging in the ammeter in series with the positive side of the ammeter being closest to the positive of the power pack, and I'm putting in a light bulb as well. Now I'll place the magnet onto the digital scales, and that will be very, very useful to measure how much force due to the motor effect. So the horseshoe magnet goes onto the scales, and I'll actually don't need the rheostat, so I'm going to take that out of the circuit. There's enough resistance in the light bulb, although it does heat up as it glows. It does change the resistance somewhat, but if I put in the alligator clips and clip that to the wire, the straight copper wire, I want to make sure that the circuit works. So I'll give it a test run. You can see the light going on, current's going through the wire and through the ammeter. So I'm ready to start the experiment, which is to determine the motor effect. I'll make sure the scales are zeroed, and I'll put the wire into the magnetic field, and I'll turn it on and see what happens. Now, first thing I can see is that there is a reading of 0.58 grams and 1.6 amps. Now, I want to make sure it's zeroed a second time. Just check it a second time, and looking at the reading there, it's 0.56 grams and again 1.6 amps. And I'll do it a third time, and this is 0.60 grams and again 1.6 amps flowing through the ammeter. I now want to change the voltage. The first voltage was 8 volts. I'm changing it up to 10 volts, putting the wire in the magnetic field, switching it on, and measuring now. The current is 1.8 amps and the reading is 0.70 grams. I'll do that a second time just to check. So I'll turn it on, and I can see that the reading is 0.70 grams and again 1.8 amps, and I'll do it a third time. When I turn it on, the reading now is 0.68 grams and it's still 1.8 amps. I want to change the voltage now to 12 volts. That's the maximum voltage on this power pack. It's DC, of course. And turn it on, and the reading is 1.9 amps and 0.77 grams. And I'll turn it on again, and this time the reading is 0.75 grams and again 1.9 amps. And turning it on a third time, reading is 0.75 grams again and 1.9 amps. So here I have the motor effect data that we've just collected, and a table of the voltage that I set on the power pack, the current through the ammeter, and a calculation of the resistance using V equals IR. And then I've got the three trials, mass 1, mass 2, mass 3, and the average mass of those three. And from the average mass in kilograms, I've then calculated the force downwards, which is its weight. So force equals the average mass times 9.8. the length of the wire in the magnetic field, the little magnet's only 2 centimetres across, so it's 0.02 metres. And using the formula F equals BIL, that's F for force due to the motor effect, equals B, the magnetic field in Tesla, times the current in amps, times the length in metres. Or rearranging, we could get B equals F divided by I times L. In this case, the magnetic field of that little magnet is about 0.19 Tesla. Here's a graph, and when you look at the graph, it's amazing. Even though we have only 3 data points, it's a straight line graph. So we have a linear relationship between the force and what we're changing current in the circuit for 3 different times. So that's the motor effect, and we've made some changes to the current going through the wire, and we've seen how that affects the force that's caused by the motor effect. I'm Mr. Mac. Thanks for watching.